the light and power system was the most important financial area of European world industry. Getting the right answer to problems of electric light and electric power meant big bucks worldwide. The problem the industry faced seemed scientifically trivial. What they wanted was to get the maximum amount of light out of a bulb for the minimum amount of electric energy going in. So the physicists were asked, do some sums and calculate what the relationship is between the amount of electric energy heating up a piece of metal wire and the amount of light coming out when that wire starts to radiate. No one thought that this was going to be a deeply important theoretical problem. It mattered to people's bank balances. It didn't seem to matter to physical theory very much. The man the industry turned to was a German physicist called Max Planck. Planck looked at Maxwell's celebrated equations, which described the relationship between light and energy. It was then that he had a shock. What these equations suggested was that the more energy you put in and the hotter the system got, the more light and heat it should radiate. Maxwell's equations had predicted that the energy levels would continue to build up infinitely until an object was radiating a catastrophic amount of light and heat. And it would atomize. But this simply isn't true. Think about what happens, for example, when you have a metal bar just resting on the fire. As it starts to get hotter, it begins to glow, initially just red, and then all the other frequencies begin to kick in. So it goes from red through blue to white heat. But no matter how hot it gets, it's never going to explode. This was a prediction from Maxwell's theory that completely failed. The apparently infallible Maxwell had made a mistake. It was a body blow to physics. As Planck tried to untangle what was going on here, he came up with an idea that was completely counterintuitive. Now, because Maxwell thought light was a wave, Maxwell reckoned that when bodies got hotter and hotter, there was absolutely no reason why they shouldn't emit more and more light. Planck then came up with a really cunning scheme to try and make the theory fit the data. Planck's problem was similar to the one Thomson had faced. Thomson had had to decide whether cathode rays were waves or particles. Planck faced an identical dilemma and came up with an extraordinary solution. What Max Planck was saying, and for him it was a quick technical fix, was that sometimes light seems to be behaving like a wave, but sometimes it seems to be behaving a bit like a particle. Now, after a bit, it quickly emerges that that's a really revolutionary idea. It completely undermines the basis of modern physics, because light turns out to have a split personality. It has a wave nature on Mondays, Wednesdays and Fridays, as one of the physicists said, and a particle nature on Tuesdays, Thursdays and Saturdays. Suddenly, young physicists had a big, new, world-shattering problem to work on. And they'd staked their careers on trying to understand light schizophrenia. Everything in physics that had been taken for granted was now up for grabs, and every ambitious young physicist wanted a piece of the action.
Abstract atomic physics developing at present will one day fit more it turned into one of the most exciting and creative periods in the history of science. Quantum physics was born.
Anyone who is not shocked by quantum theory has not understood it.
Planck's revolutionary explanation of light forced a fundamental rethink of the basic properties of matter.
Scientific knowledge has been enormously extended, and theoretical knowledge has become vastly more profound every department.
And what began to emerge was a whole new world of tiny subatomic particles no one until now had ever imagined could exist. To Thomson's discovery of the electron were added new particles like neutrons and protons.
This zoo of particles was just impossible to pull together. Physicists, for their meat and drink, night and day, tried to work out a better story about how these things could be pulled together. And the problem didn't just stay inside physics labs. No, physicists would write science fiction stories, make movies and plays to try and get the public interested. And they did.
Protons are creaking and chattering, electrons are rolling and clattering, light comes rushing with a wince. All this nonsense makes no sense, no.
The bubbling excitement eventually resulted in a completely different picture of what the atom is like. It's like a planetary system. There's a central nucleus stuffed with neutrons and protons, and around that nucleus orbit the negatively charged electrons. But what really mattered was that this atom was bubbling with energy. The atom itself could be an inexhaustible source of power. A new physics was born, a physics of the atomic age.
Atomic physics gave us nuclear fission. A terrifying new power was born. Out of the ashes emerges a completely different, completely new vision of what light really is like. And it's a very surprising one, because it's a vision of uncertainty. Not at all a mechanical world in which effects follow causes in a rigorous chain of consequences. This is the worldview of modern quantum mechanics. A worldview in which light shifts its character between wave and particle. It has completely changed the way we think about light, and it's completely changed the way we think about the world. Ironically, the more we've uncovered its mysteries, the greater those mysteries have grown.
Next on Light Fantastic, how light gave us the trickery of cinema and Einstein's truth about the universe.
Powerful drama coming up tonight. Two psychiatrists disagree about the best care for a black patient who thinks he's the son of Idi Amin in Joe Pennell's Blue Orange. Next.